Hello, my name is Nicholas Chaimov from ParaTools. This presentation accompanies the poster Multi-Platform SYCL Profiling with TAO. In this presentation, I'll briefly describe the need for a cross-platform performance monitoring tool supporting SYCL. I'll then introduce TAO, an open-source, cross-platform performance monitoring tool. Finally, I'll describe our initial work supporting SYCL profiling on NVIDIA GPUs using HIP-SYCL and CUPD, supporting SYCL profiling on AMD GPUs using HIP-SYCL and ROC Profiler, supporting SYCL profiling on Intel GPUs with an OpenCL backend by wrapping the OpenCL library and using the OpenCL profiling interface, and finally, supporting SYCL profiling using the Intel OneAPI Level 0 tool interface. A major challenge in high-performance computing is performance portability. Using abstraction layers like SYCL, applications can be developed which can target, with the same codebase, different execution environments such as traditional CPUs, many-core accelerators, and GPUs of various architectures such as those from NVIDIA, AMD, and Intel. However, cross-platform code produced in that way will not necessarily provide acceptable performance on multiple platforms. We want code to be not just portable, but performance portable as well. Performance analysis tools are needed to evaluate performance of SYCL applications. Vendor-provided tools are generally restricted to operating only on the hardware of that one vendor, and are therefore not suitable for evaluation of cross-platform performance. Our goal in this project is to provide a cross-platform performance tool for a cross-platform programming model. To develop such a tool, we have chosen to extend the TAO performance system. TAO, or Tuning and Analysis Utilities, is an open-source performance monitoring tool focused on high-performance computing applications. Under development for more than 25 years, it provides an integrated suite of performance tools with functionality ranging from instrumentation of source code, measurement of application timing and hardware performance counter data, and analysis and visualization of performance data. The TAO framework architecture is organized into 3 layers: instrumentation, measurement, and analysis, where within each layer, multiple modules are available and can be configured in a flexible manner under user control. TAO has been designed to support integrations with runtimes and application frameworks, which have been used in the past to integrate with MPI runtimes to receive data from and provide data to runtimes over interfaces such as the MPIT tools interface. A consistent goal of the TAO project has been to support all major technologies in use on leading HPC systems. With SYCL growing in prominence, particularly following the adoption of Intel's data parallel C++ as the preferred programming model for the upcoming Aurora system at the Argonne Leadership Computing Facility at Argonne National Laboratory, we have begun a project to add to TAO cross-platform support for the instrumentation and measurement of performance characteristics of SYCL applications. TAO supports 2 primary approaches to measurement. Profiling characterizes the behavior of an application in terms of aggregate performance metrics. Profiles are typically represented as a list of various metrics, such as wall clock time, and associated statistics for all performance events in the program. The most basic and standard type of profiling is called flat profiling. If TAO is being used for flat profiling, performance measurements are kept for interval events only. For instance, flat profiles will report the exclusive performance, such as time, for a routine, as the amount of time spent executing that routine exclusively. An alternative to flat profiling is call path profiling, which disaggregates performance data according to the unique call graph through which a given function or kernel came to be executing. While profiling is used to get aggregate summaries of metrics in a compact form, it cannot highlight the time-varying aspect of the execution. To study the post-mortem spatial and temporal aspect of performance data, event tracing is used, whereby each individual entry to or exit from a function or kernel is recorded along with a timestamp and potentially other metrics. In order to observe performance, additional instructions or probes are typically inserted into a program. This process is called instrumentation. Instrumentation, or direct measurement, can be introduced in a program at several levels of the program transformation process. For example, regions of interest could be manually instrumented by the application developer, automatically inserted via source transformation, inserted during code generation by the compiler, or inserted after compilation through binary rewriting. In the case of SYCL profiling, we rely on direct instrumentation of the runtime through runtime-provided tool libraries. Another mechanism that can be used to collect performance data is sampling, or indirect measurement. When using this technique, Periodic interrupts are set up during program execution. Once enabled, an interrupt handler is invoked when a certain duration of time elapses. By checking how often certain functions or kernels are observed during these periodic interrupts, the overall proportion of time spent in a given function or kernel can be estimated. We do not currently support sampling of SYCL code running on accelerator devices, but are investigating how such support could be provided in the future. Using the different instrumentation and measurement techniques available in Tau, and by measuring different metrics, Tau is able to answer many questions about the execution characteristics of applications. The performance questions that Tau can be used to answer include how much time is spent in each application routine at outer loops, and what is the contribution of statements within loops? How many instructions are executed in these code regions, and what do hardware performance counter data reveal about the mix of those instructions? What is the memory usage of the code and the I/O characteristics of it? What is the extent of data transfer between a host and a GPU or other accelerator device? What is the contribution of each phase of the program? What is the contribution of different classes of operations within a program? And how does the application scale? That is, how does the runtime change as the data size or core count changes? Interpreted languages and runtime environments present an interesting target for Tau integration because they often provide instrumentation APIs through which performance data can be captured without requiring modification of the application code. We've previously developed integrations with other runtimes that provide tool interfaces, including OpenCL, NVIDIA's CUDA, and AMD's ROCm. In this project, we have leveraged these existing integrations, building upon them to support instrumentation of SYCL applications which use those runtimes as backends. Our proof-of-concept implementation of SYCL profiling on CUDA devices uses HipSYCL, an open-source SYCL runtime with multiple backends. To capture CUDA host and device events, we use NVIDIA's cupd library. With cupd, Tau receives synchronous callbacks whenever the HipSYCL runtime makes host-side calls, and also asynchronous callbacks when device events, such as kernel executions or memory transfers, occur. However, since the CUDA kernels actually executed on the device are compiler-generated from the SYCL code, merely recording the events provided by the cupd results in a loss of contextual information, so that it is unclear what parts of the user's code are responsible for a given CUDA-level event. To address this issue, we use phased-based profiling in Tau. Phase profiling is an approach to profiling that measures performance relative to the phase of execution. Internally, phase profiling support in Tau builds on similar mechanisms used in callpath profiling. A phase event, enter and exit phase, activates special processing in Tau to record the transition between phases. With phase-based profiling, we can observe the time spent in all routines that are called directly or indirectly within a phase, which here corresponds to regions within SYCL code. To do this, we instrument the HipSYCL runtime to start a phase when the backend queues a kernel for execution, and associate the cupd correlation ID of the kernel with that phase. When the runtime enqueues a kernel, cupd activity push external correlation ID is used to associate that kernel with its calling context in the SYCL code, allowing the profile to include that context. Our proof-of-concept implementation of SYCL profiling on AMD devices also uses HipSYCL, using the ROCm backend. To capture performance data for ROCm kernels, we use AMD's ROC Profiler library. That library functions similarly to cupd, providing callbacks for kernel executions and memory transfers, which can then be used by Tau to record kernels. However, unlike cupd, ROCm Profiler does not provide a mechanism for an application to specify an external correlation ID. As a result, a different mechanism is needed to associate GPU events with the SYCL code which corresponds to the runtime-level ROCm event. We have investigated several mechanisms for expressing such correlations. The most reliable mechanism we have discovered is to use ROC Profiler interceptions. The intercepting API provides a callback when a kernel is dispatched to an HSA queue and permits arbitrary user-provided data to be attached to the callback. The HipSYCL runtime is instrumented to start a phase when a kernel is queued. The interception callback records the kernel dispatch record and phase so that the later asynchronous completion callback containing profiling data can be correlated back to the SYCL code. Enabling the intercepting API does have the drawback of serializing kernel dispatches, so we are continuing to evaluate other mechanisms for enabling such correlation. For profiling of SYCL applications on Intel embedded GPUs, we have taken two approaches, one based on profiling the generated OpenCL kernels underlying SYCL kernels in Intel's SYCL runtime, and the other based on Intel's OneAPI Level 0 API. A common technique to instrument library routines is to substitute the standard library routine with an instrumented version which in turn calls the original routine. For the OpenCL backend, Tau interposes a library wrapper using LD preload or other mechanisms to replace the OpenCL API functions with its own wrapper functions. These force the setting of CLQ profiling enable when command queues are created and record host-side function calls. Wrappers for synchronization points automatically retrieve the OpenCL profiling events and record the events. For events that correspond to host-side operations, the wrapper function starts a timer, records relevant metadata as a context event, executes the underlying operation, and stops the timer. For events that correspond to kernel executions on the GPU, the wrapper, when a synchronization point occurs, retrieves timing data through the OpenCL profiling interface and records them. The event names contain mangled C++ names corresponding to the originating C++ code, which are demangled to provide context. We have also investigated the use of Intel's pre-release OneAPI Level 0 API, which provides an API for tracing, metrics, and program instrumentation. Like ROCm Profiler, the current version of the Level 0 tools interface does not provide an analog to CUPTI's external correlation IDs. However, the event names contain sufficient information to determine at least the class which originated the kernels, if not specific line numbers. Trace markers do allow for user-provided data to be inserted into the event stream, however, which could be used to record context data from the runtime into the event stream, which would then be provided inline with other events to Tau as it processes the incoming events. We expect to make more use of the Level 0 Tools API as OneAPI development continues. Tau is available for download at tau.uoregon.edu. If you have any questions about this presentation, the use of Tau with SYCL applications, or any other aspect of Tau, please contact us by email at support@paratools.com. Thank you.